let's prove the following result, that every infinite subset E of a countable set A is countable. Okay, so let's recap. What is a countable set? A countable set is a set that can be put in correspondence, okay? It's equivalent to the natural numbers. The natural numbers, 1, 2, 3, and so on, okay? If we want, this is a bijection, it's a one-to-one and onto correspondence. So we could say that the elements in A can be arranged in a sequence, okay? If you want to say that way. So let's prove the theorem. Now we know that E is infinite, okay, and it must be it's a subset of A, and because A is countable, therefore we can arrange the elements in A as a sequence. The elements of A can be arranged as a sequence. Okay. So that's the main hypothesis. We are assuming that E is a subset and that A is countable. So we now need to relate the two things. But for now, we know that all elements in A can be arranged as a sequence. Let's give it a name. Let's call it Xn. Okay, this sequence Xn is like an index. Okay, all the elements are ordered and they are indexed by the number n, that is a natural number. Now, let's do a picture here, even if it's not very realistic, but let's say we have here the elements of A, okay? And then we are going to pick some of them that are going to be elements of E, okay? Of course, these sets are infinite, okay? But anyway, so what we are going to do, once we have the elements of A ordered as a sequence, we are going to be like going element by element, following the sequence, and then look at the times where we enter the set E with that sequence. Okay, every time we enter in the set E, we record that. So how are we going to define that? We are going to create a subsequence, okay? Well, let's call it sequence. Let's call it also sequence because a subsequence is a sequence anyway. So let's create a sequence in K of numbers, okay, that are defined in the following way with this property. To complicate it, a sequence nk such that, let's keep it simple, and here comes the property. Let's start with n1, okay? N1 is the smallest number in n, the positive integers, the natural numbers, such that x n1 belongs to E. So let's go to the picture. So we have our sequence here that lists all the elements of A, and boom, suddenly one of them is in E. So this element here, it's the first one, so this would be X and 1. Okay. and that gets recorded. And now we can let the program run. Then we will have n2, which is some number is the smallest number in n bigger than n1 such that xn2 belongs to E. That means, remember we were going through A and suddenly entered E, and maybe we left, maybe we, in this case, in this picture, boom, the next is also in E. So that one is the smallest number in N, bigger than N1, such that xn2 belongs to E. So that's xn2. In this example, then the next one would be out, and then we will be back. Let's make it a couple of them. Then a couple of them would be out. Then we would have xn3 and so on. You see the logic? So we can do this many times, and then we will have chosen at some point nk minus 1, and then define our nk, which is the smallest number in n that is larger than all the previous ones, n1 and 2 all the way through nk minus 1. Okay, and such that xnk belongs to E. Okay, and then we keep constructing the sequence this way. Okay, it's an infinite set, so this process will never stop, but this gives you an idea of how to construct any element of this sequence. Now, we are going to define the bijection as f of k, okay, is x and k. And this is for k equal 1, 2, 3, and so on. Okay, for you give me a number, a natural number, like 17 million. And following this process, I will be able to tell you what is the 17th millionth element in the sequence, in the original sequence for A, that is in E. Okay. So doing like this, we have a one-to-one correspondence between E and N, or if you want, we have shown that E is in a relation with N, okay? And that is all we needed. Once we have been able to prove that is equivalent to N, we are done, because that means they are the same cardinality, okay? This means that E is countable. Okay, so again, every infinite subset E, here it's very important that it's infinite, because if it's finite, it doesn't count, no pun intended. So every infinite subset E of a countable set A is countable. But now this has a nice consequence. Here we are done with the proof. This has a nice consequence. That is the fact, this is another theorem. Whenever we have an uncountable set, it cannot be a subset of a countable set. Can be a subset of a countable set. Okay, this is a result, a theorem, but whenever you have a result that is a consequence of a previous theorem, you call it a corollary. Okay, you write it. Corollary is a consequence. Typically, you call corollary a result that is a consequence, a direct consequence of a theorem that you just stated. Okay, it establishes a ranking of importance in your results. So this is saying that whenever you have a countable set, for example, the rational numbers, there is no way you can find a subset of the rational numbers that is uncountable.